Okay, so a special case of non-equilibrium sorption can be viewed or really an extreme case, can be viewed here. And what we've seen is that in non-equilibrium sorption we have a chemical reaction in a fluid with material on the wall of a conduit or wall of pore space, and the reaction can go one way or it can go back and forth. But in any case, there's a reaction that causes material that's in the fluid to be deposited on the solid surface. And so if that process continues, then the material on the surface will build up, and eventually there'll be enough mass there so that it will start to affect the flow. And so then we have an interesting process where we've got chemical reactions and flow, and the processes are coupled so that the fluid flow is required to bring the constituents of the reactions to the site of the reaction, but then the reactions themselves modifies the geometry that affects the fluid flow. So here are some cases where that occurs. These are some pipes that people cut open, and you can see that there's been some kind of iron material deposited on the wall of this pipe, and here's some grayish material, and I don't know what this is. It looks pretty nasty. Some kind of gooey. This looks like some kind of biomaterial. There's a little hole right there where I guess there was a little bit of flow. But obviously these are clogged up pipes. And we can see a variety of other examples of this process. And here's one where there is plaque or various deposits that occur in arteries and plug up the flow in arteries. And that causes some pretty severe medical problems. This is a thin section of sandstone, and these grayish grains are quartz sand. And what's happened is the quartz formed these pore spaces between them, and these pore spaces were cemented with calcite. And presumably what happened is the calcite was deposited first along the wall of the pore, and then there was fluid flow that brought in more of the components of the calcite, and that they precipitated out and slowly close up the pore, much like this pore is being closed up. So this is an example of the process occurring in rocks. And so another application that actually we might be seeing here is shown here with a biofilm. And in this case, we've got a solid substratum and some fluid here, and a biofilm is growing. And these are microorganisms in some kind of a structure, and actually these have very complicated structures that build out into the flow, and they get nutrients and compounds from the flow that the microbes use for various processes. Now, biofilms are used to treat water. They have a very important engineering role, but they also play a variety of roles in clogging pipes and other natural processes. And so basically, though, what's happening here is these films can be thick enough so that they build out into the pore space enough to affect the flow. So this is another example of this process of coupled flow and precipitation. So I'd like to set up an analysis of this process, and let me show you how we're going to do it. There'll be three main equations that describe this precipitation process really from a couple of different perspectives. And to understand where these are coming from, let's look at this conceptual model. Here's the fluid, and there are some molecules in it, and the concentration of those guys is called CF, and CS is the concentration on the solid. And just like we saw in non-equilibrium absorption, there's a reaction that takes these molecules and puts them on the surface, and maybe a back reaction that desorbs them, and we can describe that kinetically. So that's what I've done here. The rate of change of the sorbed concentration is equal to this constant times the concentration in the fluid. And so this stuff here is, so basically I think this part of it we understand. This is just a first order. It increases the concentration on the solid in proportion to the concentration on the fluid. Okay, so that will cause the concentration, the mass on the solid to build up, and we want to have some kind of limiting factor to that. And so we can do a couple of things. When we worked on this for homework, the non-equilibrium sorption problem had a desorption term here, which had a constant and a CS term. And so as the concentration here built up, you had an increase of desorption off of the surface. And so that could occur in many cases. But what I have in mind here is that this is actually a precipitation process, and this is some kind of a solid precipitate. And so it's not going to desorb as readily as molecules that might just be sticking to the surface. Um, and so that may happen, and we could put in a term that accounts for that. But what I have in mind and what I'm showing here is another way that we could have this compound come off of the surface. This is in a fluid flow, and so as the fluid flows along, there's a shear stress on the wall, and that shear could physically remove these compounds or these molecules from the surface. So the rate of which the concentration on the surface is decreasing could be proportional to that's the wall shear stress, and this is a threshold wall shear stress. And so basically the idea is that when this is positive, then we can have some, when the wall shear stress is greater than a threshold, then we could have the shear stress removing material from the wall. So I have this written as shear stress, and the way I implemented it is not through the shear stress but through the strain rate. Remember, the shear stress is equal to the strain rate times viscosity. So that's going to be a little bit different, but it's essentially, we can think of the viscosity as being in this term here. Okay, so this is just a reaction term very much like we saw for the other non-equilibrium sorption processes. Now, what we're going to do is simulate the fluid here and as a separate subdomain, and we're actually not going to include the solid as a separate subdomain like I'm showing here. So our model will really be just this region, and so we'll have the molecules that are dissolved in the water that go to be precipitated on the wall. The water is going to view that as molecules that are transported across this boundary at this flux. So whatever the precipitation rate is on the surface, that's what the flux is across this boundary from the point of view of the fluid. So the fluid boundary condition will be a flux boundary condition, and it will just be equal to the negative of this rate. Okay, so this is the precipitation rate on the solid, and the flux across the boundary is equal to the negative of that. Now, the reason that can work like that is because when we're solving problems like this, where we're treating the fluid and the solid in a kind of a macroscopic way, we're doing it with different units than we did for homework, which was done for porous media problems. When it's in a macroscopic way like this, where we actually have a surface, then if we look up here at the concentration on the solid surface, that's moles per square meter, so moles of compound per surface area. And in the fluid, it's moles per volume of fluid. Okay, so we can then, if we take the derivative of that, the rate of change of this concentration, that's moles per square meter per time, that's a mole flux. So the flux out of the boundary, that's a mole flux. That just equals the negative of this rate. Okay, so everything makes sense from the perspective of the units. So there's another equation here, and that's for this term omega. So what I have in mind is that the thickness of this layer that's precipitated here on the boundary is omega. And so as the precipitation occurs, this layer gets thicker. And so we've got a rate of change of the thickness of this layer. That is the growth rate of the precipitate layer. Okay, and that is going to be equal to this rate of change of the concentration that's sorbed times the molar volume of this compound that's precipitating out. Molar volume, as you recall, is the volume per mole. Okay, so I looked this up for calcite, and calcite is about 30 milliliters per mole. So you can look it up for other compounds and put it in there. And if you work out the units, this is moles per square meter per time, and that is meters cubed per mole. So the product of that is meters per time per second. So it's basically the velocity at which this layer on the surface is extending into the fluid flow. And so what we'll do is use this as the rate at which the boundary is moving. Okay, so we're going to set up this problem. We're going to use a geometry that looks like this. It'll be these are in millimeters, 5 millimeters long and 1 millimeter high. And we'll have 3 different physics interfaces: laminar flow and deformed mesh, that's combined as a single interface, transport, and surface reactions. And so here are the boundary conditions. For fluid flow, just fairly straightforward: no flow on either side, an inflow boundary at that rate, and a pressure boundary on this end. Transport, we hold the concentration equal to 1 at this side, and outflow, it's just outflow, no diffusive flux. We'll also have an initial condition where we set the concentration CF equal to 1 throughout the domain. This is no flux, and then this is where the reaction is going to be taking place. And so this is a flux boundary from the transport perspective, and it'll be equal to this reaction, the negative of this reaction. And this reaction is this guy here. Okay, and so then there'll be another physics, which is the surface reaction, and that will only be active right here along this boundary. And the way we'll work this is we'll have the reaction taking place along this boundary everywhere, except the reaction rate, and again, it's that expression we saw on the previous slide, we'll multiply it by a step function. So the step function will be equal to 0 here, and then it'll step up to 1 here and be equal to 1 here. And that will cause it to be non-reactive here and then reactive here. And so the reason for doing that is then we can have the fluid flow come in, have the fluid velocity distribution kind of get worked out, and the reaction takes place here after the velocity is kind of stabilized. And then the way we'll simulate this is with a moving mesh. The mesh will move as stuff gets precipitated. And so the boundary conditions for the moving mesh is that on these 3 sides, the mesh displacement is 0. And on that side and that side, we say the mesh displacement in the x direction is 0. And here we say the mesh displacement in the y direction is 0. And here we specify the mesh velocity, and that equals this expression that I just showed you, the reaction rate times the molar volume. Okay, so that's schematically how we set the problem up. And then when we put it together, we're going to first define the geometry and the physics and so on. And then the way I would recommend doing this is to first get the flow working, then the flow transport surface reaction, and then flow transport surface reaction and the deformed mesh. So get each one working and then add in the next one. So this is what it's going to look like. As the fluid flow goes along in this direction, this is the concentration. It's non-reactive here, so nothing is happening. And then once we hit the reactive zone, the concentration is going to drop in the fluid. And that's because the mass is being consumed along this reactive wall. And if we look at how the flow changes when the wall deforms, this is the wall bulging inward, and this all is precipitate here. And you can see how the flow geometry has changed. Now, one thing that I wanted to include here was the effect of shear on the erosion of material, and that's done through the equation that we saw earlier, the reaction rate equation. And I think you can see pretty clearly there's that little point right there. That would be very high shear stress right there. And so what I wanted to do is implement a way to prevent that from growing because of the high shear stress. So I implemented the shear stress as a negative term in the rate expression. And when you do that, you get a function that looks like this, or you get a result that looks like this. So let's take a look and see about setting that up. I've got a model built already. So this model has some variables that implement those equations. And here they are. The CS rate, this is that first equation that we saw. And it's the M1, which is this term here. This is the precipitation of the solid. And then M2 is the erosion of the solid. And that's multiplying a step function, multiplied by a step function, which causes the erosion to be zero until you get to a certain threshold shear stress. And it's important to fiddle around with that threshold, because if it's too low, then nothing gets deposited, everything just gets sheared off. And if it's too high, then nothing ever gets sheared off. So what I did was to plot the shear stress and take a look at the values and set the threshold value accordingly. And then I also multiply everything here by a step function that this step 1 here is it's at 0.002, so that's set at 2 millimeters, and it steps up at 2 millimeters, and basically this is what's going to, let's go here to the geometry. That's what's going to step up right here at 2 millimeters and allow the reaction to take place down here downstream and not upstream. Okay, so the geometry is simple. It's just this rectangle, and we have water in here as material, and there are these three different physics. The laminar two-phase flow is has these different boundary conditions. There are 8 boundary conditions that are specified. 4 boundary conditions for the fluid and 4 for the mesh, and they're shown here. One of the things that you want to also make sure of is when you set this thing up, the mesh smoothing type, it seems like what happens is the default is Winslow, but you need to I have not gotten Winslow to work for this problem, but Laplace works very nicely, so be sure to switch it to Laplace. Um, and so the key thing here is that for the fluid flow problem is easy. You've done this before. The mesh problem is not so easy, or at least it's not as familiar. Here are the mesh displacement boundary conditions where we fix the displacement on the mesh, and here are the y displacements being fixed, or actually this is fixing both of them. And then this is where the action is occurring, the prescribed mesh velocity. And this is the mesh velocity. It's a term called growth rate. If we look up here under variables, the growth rate is this CS rate times the molar volume. So that's consistent with what we saw in the PowerPoint. And if we look at let's look at transport. The aspect I think that's different here is that we have this flux boundary along this boundary where the deformation will occur, where the precipitation will occur, and that's tied into this variable. The inward flux is going to be this thing called mass out fluid, and that's a variable that's shown right here, and it's just the negative of the CS rate. So if we go back to the PowerPoint, you can see where this is all coming together. So that flux boundary that we just saw is minus this dc dt, which is that term. That's CS rate. So CS rate is that top term, minus CS rate, that's the flux, and then CS rate times molar volume is the rate of deformation. Okay, so let's go back here. There's the flux, that mass out fluid, and then the surface reaction. This is another interface that you can use that is just designed for surface reactions. We're only using it for this surface, and we're putting in, now let's expand it. We put in, I added here this boundary condition, reaction, and that allows me to specify this reaction on the boundary, and it's that first equation that we saw. Okay, so those are those three specifications of those basically the same boundary is being specified three different ways in these three different physics. One is, this is specified as a mass flux to remove mass from the fluid. This is surface reaction to consume the mass by a precipitation reaction. And this is used to deform the mesh, which will cause the mesh to move upward and deform the geometry. Okay, so here's what the results look like. Here's the initial conditions. It actually shows a preview of what the concentration distribution will look like. So early on, we've got something that looks like this, but after the process goes on, here's the buildup of the material, and this is the final result. And if we kept it running, it would continue to build up into the flow. We can look at the video of this, and there we see the this is the velocity, and so the velocity is increasing in this area where the cross-sectional area is decreasing. And you can also see that this process of precipitation is affecting the flow as the flow moves up and goes around this. Now, one of the things when we go and include the shear stress, I wanted to know what the shear stress was. So I took a look at the shear stress early in the simulation, and it's a bit less than 5. But then after that bump starts to grow, then we have a place where the shear stress is low before the bump, and then here's the bump. This is the peak of it, where the shear stress is really high, and then there's a place where it's a bit lower on the downstream of the narrowest point. So what I said was, oh well, I think what I'd used was a threshold of 7, and so what I said was, well, if the shear stress gets greater than 7, then the material has more difficulty precipitating onto the wall. And so if you do that, then you kind of subdue the growth of the precipitate there. Let's see. If you do that, you'll suppress the growth right here, where the shear stress is highest. And so the way that you'll do that is by adjusting this term called threshold, and that's then implemented in this step function. That's where this step takes place, and the threshold is saying that at lower values of that shear stress, then this equals 0, and at higher values it equals 1. So when I take that step function and use it right here, then I cause this negative part of the rate the rate term to be 0 when the shear stress is less than the threshold, and this term is equal to 1, so this M2 term is able to be whatever it is when the threshold is greater than in this case 7. Now what you'll do for the lab is to set up a problem with a different geometry, with an axially symmetric geometry. And I think probably what you want to do is you want to use this threshold eventually, but you want to check out the shear stress that you're getting and adjust the value of it accordingly. In the video, I suggest using 7, but then as I checked it after that, I think 7 is too low. Probably something more like 10 is going to be better. But plot it out and take a look at it just like I showed you.